Okay, the last equation that we derived is called the complex pointing theorem. Okay, just for your understanding, let me write one more time the complex pointing theorem. And okay, and the complex pointing theorem is this E cross H complex conjugate by ds is equal to j omega integral over the volume V epsilon E complex minus mu H complex dV minus the integral over the volume V E multiplied J0 complex conjugate dV minus, scale down a bit, so minus the integral over the volume V of sigma multiplied by electric field intensity, the complex conjugate of electric field intensity dV. So, as we have mentioned at the beginning of the previous lesson, when using the complex pointing vector, the use of complex pointing vector is for the purpose of calculating time averaged quantities. It is therefore more useful to write this relation as two terms as following. So 1 over 2 the real part of the integral over the closed surface of complex pointing vector ds is equal, the real part is equal to this part, is equal to 1 over 2 multiplied by the minus 1 over 2, because here we have minus 1 over 2 of the integral over the volume V of E J0 complex conjugate dV minus integral over the volume V of sigma multiplied by E multiplied by E complex conjugate dV. Of course, here also should be 1 over 2. Sorry. Here should be also 1 over 2. Okay, let me move it a little bit, and I will add here 1 over 2. So 1 over 2. And 1 over 2 of imaginary part of this integral, or the integral of complex Poynting vector ds over the closed surface S, is equal to omega is equal to omega, so multiplied by the integral over the volume V of epsilon multiplied by E multiplied by E complex conjugate over 2 minus mu H multiplied by H complex conjugate over 2 of dV. Okay, let me highlight these two equations. So this equation, or let me say equation number 1 and equation number 2. Equation number 1 gives the real power balance in the volume. So the left-hand side of the equation number 1 is the net outward flow of power through the surface enclosing the volume, and the first term of the right hand side is the net source power. For example, in this case the source is outside the volume, that's why we have sign negative sign. And the last term of equation 1, which is this term, is a dissipated power in the volume. And as we already know, this term is positive for the receiver case and negative for the transmitter case. And respectively, so E multiplied by J complex conjugate is positive for receiver and negative for transmitter. That's why the whole term correspondingly is will be negative for receiver and will be positive for the transmitter case. Well, if this term is positive for the receiver case, because of this minus, the whole term will be negative, and the whole term is negative for the receiver case, and the whole term is positive for the transmitter case. Okay, and the second equation number 2, which is the last equation in at your screens, is the balance of reactive power. So it shows it is the rate of flow of reactive power across the surface. The right hand side gives the time averaged reactive power. Okay. Well, let's see one example. Consider again the magnetic and electric fields obtained in example 12.8, but now these are given in the frequency domain as E equal to minus Y, eta 0, H 0, e to the power of minus jkz, and H equal to X, H0, e to the power of minus jkz, where H0 is given and frequency is given, propagation is in free space, and Z is the vertical direction. Calculate the time averaged power density in this wave. Write a stored electric and magnetic energy densities separately. Okay. I forgot one point. So let's look to the last two equations, and stored time averaged magnetic and electric energy densities can be written as so. Stored time averaged magnetic and electric energy densities. Okay. So stored time averaged magnetic energy density can be written as so. Let me write in blue. W magnetic averaged is equal to 1 over 4 mu H dot H complex conjugate and stored time averaged electric energy density can be written as respectively 1 over 4 epsilon E multiplied by E complex conjugate. So okay. First, stored time averaged magnetic energy density, and the second is stored time averaged electric energy density. Okay, first of all, calculate time averaged power density in the wave, and second, calculate stored electric and magnetic energy densities separately. So time averaged Poynting vector can be calculated using the equation that we have derived in previous problem. The 1 over 2 of real part of electric field intensity cross complex conjugate of magnetic field intensity. First of all, we need to compute the complex conjugate of H. So we know that if we look to H, H0 is real and complex conjugate of e to the power of minus j kz, complex conjugate of this is e to the power of plus j kz. And we may say that complex conjugate of H is x. H0 remains e to the power of plus j kz. J kz. And now let's try to compute the cross product of E and H and take the real part of this cross product. Okay. P average time averaged Poynting vector or time averaged power density is equal to 1 over 2 the real part of E multiplied by H. So the real part of E cross H complex conjugate. here E is equal to this, we write minus y eta 0 h0 e to the power of minus j k z cross h complex conjugate is, we have found x multiplied by h0 e to the power of j k z. Equals. So ejkz, ejkz, one of them is minus, another is plus, simplifies. So minus y cross x gives us z, and what we have equals 1 over 2, so equal 1 over 2 z eta 0 h0 squared. So the time averaged power density in the wave, time averaged power density is, we have found z eta 0 h0 squared over 2. Now we may put the numeric values and compute. Okay, 377 multiplied 25 squared over 2, and this is equal to over 2 okay. Z 117.8 multiplied 10 to the power 3 of watt per meter squared. Okay. And now the second part of our problem. The second part of our problem, write stored electric and magnetic energy densities separately. Here we may see the formulas for stored electric energy and for stored magnetic energy, and we directly put the numeric values to these formulas. Okay, let me put here. First, in order to, so first we compute stored time averaged magnetic energy density is 1 over 4 multiplied by, so in our case is mu 0, because we are dealing with the free space, mu 0 multiplied Okay, the H is in our case x multiplied H0 multiplied e to the power of minus j kz multiplied H complex conjugate is x multiplied H0 multiplied e to the power of plus j kz. And this equal, and this is equal to 1 over 4 mu 0 multiplied H0 squared. Yeah. Yes. And what about time averaged electric energy, time average stored electric energy? So 1 over 4 epsilon 0, and electric field intensity is given as minus y eta 0 h0 e to the power of minus j kz multiplied. Complex conjugate will be minus y eta 0 h0 e to the power of plus j kz, and this will be equal to 1 over 4 eta 0 epsilon 0 h0 squared. So eta 0 epsilon sorry, eta 0 squared, because we have 1 eta 0 and 2 eta zeros. Okay, and if we compute the numeric values, 1 over 4 multiplied mu 0 is 4p 10 to the minus 7 multiplied h0 is 25 squared. Okay, okay. 4 simplifies. Pi multiplied by 625 is this, 10 to minus 7. Okay, divided by 1, 2, 3. 1.96, 1.96 10 to the power of minus 4 joule per meter cube. Stored time averaged magnetic energy. Now what about the stored time averaged electric energy? So we compute 1 over 4. So eta 0 is 377 squared multiplied epsilon 0 is 8.8 okay, 8.854 10 to the power of minus 12 multiplied h0 is 25 squared, and this will be equal to 1 over 4 multiplied 377 multiplied 377 multiplied 8.854 multiplied by 625 and divided by 8. Okay, 8 times 1, 2, 3, 4, 5, 6, 7, 8. 1.97, 967 or 966, sorry, 966, 10 to the power of minus 4, again, joule per meter cube. Okay. Well, in the page of 627, there are two another exercises. Try to do these two exercises at home, and in the next lesson we will discuss this exercise and we move to the next section. So for today the lesson is over.